Today I present about tree of claims search with multi-agent language models. Contents are followed. Drafting and revising patent claims is a critical task that directly affects the legal scope, technical breadth, and commercial potential of intellectual property. Patent claims requires the simultaneous considerations of precise legal wording, preservation of technical coverage, and novelty over prior art. However, manual processes are resource-intensive, costly, and inherently inconsistent. Advances in foundation models and LLMs have expanded automation possibilities across domains such as medicine, law, and etc. However, existing LLM-based patent drafting and revision approaches mainly rely on single-shot or few-shot paradigms, which lacks the iterative and structured reasoning process. Existing approaches often fail to adequately balance the complex interplay among legal scope, technical specificity, and linguistic precisions. Therefore, this study highlights the need for a new claim optimization framework that combines the generative capability of LLMs with structured search and controllable revision procedure. This study aims to redefine patent claim optimizations as a structured search problem and improve novelty, scope preservations, and legal robustness through the ToC framework, which integrates MCTS with multi-agent LLMs. This study formalized patent claim optimizations as a structured search problems and proposed the ToC framework. It designed a collaborative multi-agent architecture consisting of editor agents and examiner agents. Through real-world patent claim revisions experiments, this study demonstrates that ToC outperforms conventional zero-shot and few-shot LLM-based approaches. GPT-4 are increasingly being used in patent-related tasks, including patent claim drafting, claim revisions, and response of office section. However, existing LLMs have limitations in controllability over output structures, claim scope, and legal consistency. Domain-specific fine-tuning can improve linguistic fluency, but it doesn't fundamentally resolve the core issues of controllability in claim revision. Recent benchmark shows that even strong LLMs still require iterative human refinement to achieve full legal robustness. Recent research has shifted from simple generation-based approaches toward feedback-driven claim revision. Autopatents and Evopat employ multi-agent frameworks, but their editing operations are often opaque and non-deterministic. ToC is designed so that each claim revision is performed through an explicit and justifiable stepwise editing process. Multi-agent LLM frameworks enable multiple specialized agents to collaborate and critique one another, thereby producing more coherent reasoning outcomes. These structured approaches contribute to improving LLM reasoning quality. Most existing multi-agent systems are designed for open-ended tasks. Unlike general task generation, patent claim revisions require fine-grained control over legal criteria, claim scope, and technical accuracy. Unlike prior systems that only generate the final output, ToC provides the entire revision history in an interpretable and auditable form. Search algorithms are useful for LLM-based text generation tasks that require planning, constraint certifications, and multi-objective optimization. These approaches, together with evolutionary or reinforcement learning-based strategies, enable more controllable and reliable text generation. Applying search-based optimizations to legal tasks, strict constraints related to contextual coherence, legal compliance, and scope preservation. ToC defines atomic edit operations as move in search trees, becomes a plausible and traceable editing trajectory. The O-gating mechanism based on the examiner agent's variance-based confidence score filters out highly uncertain revision candidates and reduces the risk of erroneous edits. Given an initial claim and a set of prior art documents, this study aims to generate revised claims that maximize novelty over the prior art while preserving the technical scope of the original claims. The claim revisions process is modeled as a sequential decision-making problem. Each state represents the claim configurations at time step t. Each action represents an atomic editing operations for revising the claim. Prior documents may include not only textual information but also figures or images that provide contextual information relevant to the claim. The action space A in ToC consists of 10 atomic edit operations. To ensure semantic validity in claim revision, precedence relations among editing operations are defined. For example, adding a novel technical features must precede synonym replacements to maintain semantic coherence. The final objective is to find the optimal editing sequence A star that maximizes the expected cumulative rewards based on the rewards functions, which evaluates the quality of each modification. This formulation shows that ToC doesn't generate a single revised claim directly, but instead searches through multiple editing paths to identify the best claim revision trajectory. ToC is a search-based framework that combines MCTA's multi-agent collaborations and uncertainty control for patent claim optimization. The overall process consists of four phases: selections, expansion, simulations, and backpropagation. Each node in the search tree represents a claim state and is expressed as n. At here, C denotes the claim text, O denotes the edit operation sequence, R denotes the cumulative rewards, and the O denotes the uncertainty value. In the selection phase, the search expands toward the most promising path by selecting the child node. In the expansion phase, the examiner agent identifies claim elements that require revision. In the simulation phase, a complete revised claim is generated through rollouts from the newly added node. And in the backpropagation phase, the reward of the simulated claims is propagated back to its parent node. O-gating removes highly uncertain search paths or flags them or human experts view, thereby controlling potentially erroneous revisions in advance. ToC performs optimal claim revisions through a multi-agent structure in which the examiner agents and editor agents collaborate. The examiner agent compares each claim element against prior art documents. The examiner agent classifies its judgments to disclosed, not disclosed, or partially disclosed. The examiner agent is designed to output results in a strict JSON format to ensure consistent parsing and evaluation. If the uncertainty value exceeds the threshold, the case is flagged for human interventions or a strategy switch. The editor agents generate atomic edit operations based on the examiner agent's feedback. The editor agents mainly revise elements disclosed by prior art while preserving the original claim scope. Revision quality is evaluated using criteria such as text similarity, scope preservations, legal readability, and technical coherence. The editor agent selects revision strategies by considering how each edit operation affects novelty, claim scope, and legal validity. The collaborate loop between the two agents ensures that each revision is legally robust and technically meaningful. ToC MCT8's search is designed to jointly consider multiple objectives: novelty enhancement, scope preservation, technical novelty, logical consistency, and uncertainty control. The weights are set as weights 1 to weight 5, encouraging ToC to increase coverage and novelty while suppressing unnecessary scope narrowing and uncertainty. Uncertainty is decomposed into optimistic uncertainty and aleatoric uncertainty. To ensure reproducibility, random seeds were fixed and each experiment was repeated 3 times. The ToC system was implemented in Python, and the LRM decoding settings were managed through a unified configuration interface. In the experiments, the ToC framework was applied to various multimodal LLMs. The model includes OpenAI, GPT-4o, and Claude 3.5 sonnets. The open source models included QN 2.45, and inference was performed locally using the Hugging Face Transformers library. All models were assigned to both the examiner agents and editor agents roles, and the same prompt structures, outputs, schema, data split, and evaluation protocol were applied to ensure a fair comparison. This study constructs a benchmark based on the USPTO Office Actions Research dataset. The dataset consists of 1,145 unique patents, 28,261 claims, and 8,418 prior art references. The processing pipeline pairs structures patents and office action, records the Alliance examiner cited prior art with rejected claims. Each claim is decomposed into semantic sub-elements. The dataset has a multimodal structure incorporating not only textual descriptions but also figure and diagrams from patents documents. To evaluate the effectiveness of ToC, the study compares it against zero-shot baseline and few-shot baselines. To ensure a fair comparison, all settings use the same input-output format, prompts, and search budget. The evaluation is conducted on a 500 sample holdout set. Additional metrics are used to assess the general robustness of the models, including JSON parsing completeness, chain entropy, image text consistency, legal readability, and token level perplexity, log L, value, and expert preference. These metrics enable comprehensive evaluations of not only generation quality but also legal robustness, format stability, multimodal consistency, and expert preference. All models equipped with ToC shows overall performance improvements rather than zero-shot and few-shot baselines. Among the closed-source models, GPT-4o and ToC archives the best overall performance. Among the open source models, QN 2.5 plus ToC performs the best. In actually generation metrics, ToC also improves over the baselines in terms of JSON completeness, log L, VLU, and lower PPL. Expert evaluations was conducted by 5 patent specialists with at least 5 years of industry experience, using novelty, legal robustness, and technical coherence as key criteria. In comparative expert evaluation, ToC revised claims were preferred in approximately 2/3 of cases where prior art was available. Error analysis shows that system control failures were the most frequent error type, including excessive branching, zero confidence decisions, missed learning opportunities, and invalid modification. The evaluation study shows that removing uncertainty, gating, progressive widening, or multi-agent collaboration leads to a clear decline in novelty coverage and overall legal quality. Sensitivity analysis shows that the best accuracy is achieved at alpha 0.6 and T max in 15. The mean reward reaches approximately 70% of its eventual gain with the first iterations and plateaus after iteration 10. This study proposed the Tree of Claims framework, which combines structured search and multi-agent collaborations for patent claim optimization. ToC model claims editing as the MCTA-based sequential decision-making task, enabling the revision process to be conducted in a more transparent and controllable manner. ToC significantly improves novelty, legal quality, and expert preference. ToC proposed a shift from passive text generations toward strategic collaborations-based claim optimizations. The multi-agent structure improved correctness, transparency, and interoperability. Future research can focus on improving such efficiency through distributed computing. ToC can be extended beyond patent claims to other structures affecting domains such as legal contracts, medical protocols. Overall, ToC is presented as a framework suitable for domain requiring high reliability, domain-specific consistency, and traceable multi-turn reasoning. Thank you for listening.